is to take your source material, really dig in, and pull out the core insight.
Yep. Cut through the noise.
Exactly. And today, we're tackling a mathematical concept that might sound a bit abstract initially, spherical harmonics. But the thing is, these are kind of unsung heroes. They show up absolutely everywhere.
They really do.
From like the smallest quantum particles all the way up to mapping the entire universe.
It's quite the range.
So think of them as these basic shapes, right, or patterns on a sphere's surface, and you can use them to build up any other pattern on that sphere.
That's the core idea.
Our goal here is to explore your sources, figure out where these patterns actually come from, what makes them so useful, and, well, where we see them in action.
Sounds good.
Okay, so let's unpack this a bit. What exactly are these spherical harmonics, these building blocks?
Well, at their heart, they're a specific set of mathematical functions, and they're defined crucially on the surface of a sphere. They are, like you said, the fundamental components you need if you want to describe anything that varies across that surface.
Okay, so if I had, say, a globe, or even just a ball, and I wanted to describe temperature differences on it, or maybe hills and valleys.
Or even how light hits it, yeah. You could represent that change in quantity as a sum, a combination of these specific spherical harmonic functions.
And what's really interesting, based on the sources, is why these specific functions work, right? It's not arbitrary.
Not at all. They actually emerge naturally when you solve some really fundamental equations in physics, especially in systems that have some kind of spherical symmetry.
And the big one mentioned is Laplace's equation.
Yeah,
that zero-zero thing.
That's the one. Laplace's equation is incredibly common. It shows up all over physics and engineering.
Where specifically?
It describes potential fields where there are no sources, like think electric potential in empty space, or gravitational potential, or even how temperature settles down inside something being heated, steady-state heat flow.
Ah, okay. So whenever things are smooth, no charges or heat sources right there.
Exactly. And when you need to solve that equation for problems involving spheres, which happens a lot, obviously you usually switch to spherical coordinates.
Right. So not just x, y, z, but distance from the center and then the two angles to pinpoint a spot on the surface, like latitude and longitude.
Pretty much, yeah. Polar angle and an azimuthal angle. And the standard technique to solve Laplace's equation in these coordinates is called separation of variables. You break the equation into different parts. Yeah. One part just depends on the radial distance, how far you are from the center, and the other part depends only on the angles, on where you are on the surface.
And that angular part, that's where these harmonics come from.
That's it, exactly. The spherical harmonics are the special functions that solve the angular piece of Laplace's equation on this sphere's surface.
Gotcha. And they're written as y with two little subscripts, L and M.
Yep. Y sub Lm Yilm, depending on the two angles, theta and phi.
Okay. L and M. What do those numbers actually tell us? Are they just labels?
No, they define the shape. They're integers. The first one, L, is called the degree.
The degree.
It basically tells you about the overall complexity of the pattern. How many features, like peaks and valleys or nodes, it has across the whole sphere. L starts at 0 and goes up 0, 1, 2, and so on. Higher L means more intricate patterns.
Okay. In M?
M is the order. For any given L, M can take integer values all the way from negative L up to positive L. So if L equals 2, M can be -2, -1, 0, 1, or 2.
5 possibilities for L at 2 then.
Right. And it generally relates to how the pattern is oriented, sort of how it varies as you go around the sphere's equator, let's say, azimuthally.
So each specific pair of a limb gives you one unique, distinct pattern on the sphere.
Exactly. And your source material also mentions how they're built, mathematically speaking. They involve something called associated Legendre polynomials.
Right. Picasso. It sounds complicated. What part do they play?
Well, you can think of it like this. The spherical harmonic yom describes variations both up-down, latitude related to F, and around, longitude related to the associated Legendre polynomial part, the Lom-Coser, specifically handles that up-down variation, the dependence on the polar angle theta. Then there's another bit, usually involving complex exponentials, that handles the around part, the phi dependence.
Okay, so they are these specific natural patterns for angular stuff on a sphere. But what gives them their real power? Why are they so useful everywhere?
It really comes down to two crucial mathematical properties, orthogonality and completeness.
Orthogonality. Okay, I think of vectors being orthogonal, like at right angles, perpendicular. How does that work for functions spread out on a sphere?
It's a very similar idea, actually. It means that each of these spherical harmonic patterns, each yelm, is fundamentally distinct and independent from all the others with different L or M values.
Independent how?
Mathematically,
Yeah.
you take two different spherical harmonics, say yum and yum, where either L is different from L or M is different from M, multiply them together, and then integrate or sum up that product over the entire surface of the sphere. The result is always zero.
Always zero unless they are exactly the same function.
Precisely. If L and MM, the integral is non-zero. Otherwise, zip. They don't overlap in this specific mathematical sense.
It's like they occupy their own unique space on the sphere, mathematically speaking, like pure tones in music. A pure C note isn't made of any G note.
That's a great analogy.
Yeah.
And this property, this distinctness, is absolutely vital because of the second property, completeness.
Completeness. Okay, what does that mean?
Completeness means that any reasonably well-behaved function or pattern you can define on the surface of a sphere, temperature map, gravitational field map, whatever, can be perfectly represented just by adding up the right amounts of these fundamental spherical harmonic functions.
So because they're complete, they form a full set, a basis. You don't need anything else. You can build any pattern on the sphere just by combining these basic Yelm shapes.
Exactly right. Just like any periodic signal can be built from sine and cosine waves in Fourier analysis, and the orthogonality we just talked about, that's what makes it relatively easy to figure out how much of each specific Yelm pattern you need.
How does that work?
Because they're orthogonal, you can isolate the contribution of each individual harmonic. You can calculate the coefficients, the amount of each Yelm needed in that sum. It lets you decompose the complex pattern into its fundamental spherical harmonic ingredients.
Just like Fourier analysis lets you find the strength of each frequency in a sound wave. Same idea, but on a sphere.
Exactly the same principle. And your sources also mention visualizing them, which helps.
Yeah, the pictures.
Right. The LM numbers relate to nodal lines, curves on the sphere, where the function's value is zero. As it gets bigger, you get more nodal lines, the patterns get more intricate, vary more rapidly.
And the visualization sometimes shows the magnitude by how far the surface is from the center, creating those lobed shapes.
Yes, that's a common way to visualize the magnitude. It gives you a good feel for where the function is large or small.
Okay, that really helps picture it. So we've got these distinct, complete building blocks for spherical patterns. Now, the really cool part, where do we actually see this in action? The sources list an incredible range.
They really do. It's because they're so efficient at capturing information spread across the sphere. Let's start small, quantum mechanics.
Okay, atomic level. The sources highlighted this strongly.
It's absolutely fundamental there. When you solve the Schrödinger equation for an electron orbiting a nucleus, like in a simple hydrogen atom, the electron's wave function, which describes its probability distribution splits, it has a radial part and an angular part.
And let me guess.
That angular part is a spherical harmonic. The indices, L and M, directly correspond to the electron's quantized angular momentum quantum number and its magnetic quantum number, which is its angular momentum's projection on, say, the z-axis.
Wow, so those pictures we see in chemistry textbooks, the s orbital being spherical, the p orbitals like dumbbells, the d orbitals like clover leaves, those shapes are basically visualizations of Yelm for different L and M.
Pretty much. They are the angular shapes described by the low-order spherical harmonics. S is del0, P is L1, D is L2.
Mind blown already. Okay, scaling up. Electromagnetism.
Yep. They're essential for something called multipole expansions. If you have a complicated blob of electric charges or some complex currents making a magnetic field, calculating the field everywhere can be tough.
Right.
But far away from the source, you could approximate the field really well by representing the source using a sum of spherical harmonics. The L year 0 term corresponds to the total charge, monopole. The L1 terms give you the dipole moment, L2 gives the quadrupole moment, and so on.
So it's a way to capture the essence of a complex source by breaking it down into simpler spherical shapes. Monopole, dipole, quadrupole.
Exactly. It simplifies the problem enormously at large distances.
Okay, zooming out even further, cosmology. The whole universe.
Yeah. This is one of the most striking applications, I think. You know the cosmic microwave background? The CMB?
Yeah, the afterglow of the Big Bang, that heat map picture of the sky.
Right. It shows these tiny temperature fluctuations across the entire celestial sphere. What cosmologists do is take that map and decompose it using spherical harmonics. They calculate the coefficients, kilomum, telling them how much of each Yelm pattern is present in the CMB sky.
And what does that tell them?
A huge amount. Analyzing the strength of fluctuations at different angular scales, different Isle values, gives us incredibly precise information about the composition of the early universe, its geometry, the seas of structure formation, inflation. It's a cornerstone of modern cosmology.
It's just amazing that the same math describes an electron's orbital shape and the structure of the entire observable universe moments after the Big Bang.
It really speaks to the fundamental nature of these functions.
What about closer to home, like our own planet?
Oh, absolutely. In geophysics and planetary science, they're indispensable for modeling gravitational fields and magnetic fields.
How so?
Satellites orbiting the Earth or other planets make super precise measurements of gravity and magnetism all over the surface. This data is almost always represented as an expansion in spherical harmonics. Analyzing those harmonic coefficients lets scientists infer things about the planet's interior.
Like what?
Like mass distribution, density variations in the mantle, the dynamics of the liquid core generating the magnetic field. Your source specifically mentioned modeling the Earth's geoid.
The geoid. That's like the theoretical sea level surface if there were no winds or tides, just gravity and rotation.
Exactly. It's a surface of constant gravitational potential, and is represented mathematically using a spherical harmonic series. It reveals bumps and dips reflecting mass concentrations below.
So understanding the lumpy nature of Earth's gravity depends on these harmonics. And say, switching gears dramatically. Computer graphics, how do they fit in there?
This is a really neat one and something many people benefit from without realizing it. In modern video games and animation, getting realistic lighting is key. Calculating how light from the environment to the sky, other objects bounces off surfaces, can be very computationally expensive, especially in real time.
I bet.
Spherical harmonics provide a clever shortcut. You can represent the incoming light hitting a point from all directions, the illumination environment, using just a small set of spherical harmonic coefficients.
So instead of calculating light from every direction separately,
You capture the overall lighting environment compactly with a few numbers. Then, when you need to calculate how much light reflects off a surface point, you can do a quick calculation using those pre-computed SH coefficients.
and that's faster.
Much faster. This allows for effects like soft, diffuse lighting from the environment, even some global illumination effects, to be rendered incredibly efficiently. It's often called spherical harmonic lighting, or used in techniques like pre-computed radiance transfer.
Wow, so these math functions are literally making games look better and run faster. That's cool. Your sources also touched on chemistry and medicine.
Right. In chemistry, beyond just atomic orbitals, they're used in computational chemistry to represent the shapes of molecular orbitals in more complex molecules,
Okay.
and also to analyze the 3D shape of molecules themselves. For example, describing the distribution of chemical groups or ligands around a central atom or protein. This is really important in things like drug design, trying to understand how a drug molecule might fit into the active site of a protein.
Analyzing shapes, and that links to medical imaging too.
Yes, it's an emerging application area. Researchers are using spherical harmonics to create mathematical descriptions of the 3D shape of anatomical structures captured in MRI or CT scans.
Like which structures?
The source mentioned the hippocampus in the brain, for instance. It's an area affected early in Alzheimer's disease.
So the idea is?
The idea is to represent the hippocampus shape with spherical harmonic coefficients. Then, by comparing these coefficients between healthy individuals and patients, or tracking changes over time, you might be able to detect subtle shape alterations that could be early signs of disease.
That's incredible potential. So looking back, atoms, the early universe, planets, video game lighting, drug discovery, brain imaging. It's really striking how this one mathematical tool ties together so many different fields.
It really is. They emerge from solving a fundamental equation, Laplace's equation, in a spherical context. And their properties, orthogonality and completeness, make them this incredibly versatile toolkit.
A kind of universal language for spheres.
Exactly. A powerful mathematical language for describing, analyzing, manipulating almost anything that happens on a sphere, no matter the scale or the specific physics involved.
It really drives home that this isn't just, abstract math for its own sake. It's an engine. It powers understanding and drives technology we use and benefit from.
Definitely. So we've seen where they come from, Laplace's equation in spherical coordinates. We've seen their key properties being distinct, orthogonal, and forming a complete set. And we've touched on just how widely they're applied across science and engineering.
Yeah.
Their importance and usefulness seem pretty undeniable. They are truly indispensable tools.
And that makes you wonder, if something as seemingly simple and fundamental as a sphere needs these quite intricate specialized functions to really describe what's happening on its surface, what does that imply about all the other shapes we encounter?
Interesting point.
Are there other complex, maybe less perfect shapes all around us, just waiting for their own unique mathematical keys to unlock their secrets and applications? It certainly makes you think about the deep connection between geometry and the tools we need to understand it.
It does. What other mathematical languages are out there waiting to be fully explored for other fundamental shapes? A great question to ponder.